In this lecture, we're going to continue our discussion of combustion reactions. In the first couple of slides here, review the basic information needed to work these problems. The first is what is the reactions we're talking about. These most commonly are reactions of a hydrocarbon fuel. Hydrocarbon meaning it's a combination of carbon and hydrogen. And it may also have a little bit of oxygen and potentially some sulfur in there. But it's a reaction of these fuels with oxygen. And the primary reactions that are involved are these, is that the carbon atoms in these hydrocarbons react with oxygen to form CO2. This is usually referred to as complete combustion. An alternative is to have carbon react with oxygen to form CO, which is referred to as partial or incomplete combustion. The hydrogen that's present in the hydrocarbon will react to form water. Any sulfur that's present would react to form SO2. These reactions here are balanced and indicate how each of the atoms would react. This reaction occurs with oxygen. The oxygen is typically provided by air. So along with the oxygen comes nitrogen, because air consists primarily of oxygen and nitrogen. And we'll assume that the nitrogen composition of the air is 79% and the oxygen composition is 21%. We're going to ignore argon, which is present in air about 1%, and all other gases. There's some new terminology we need to introduce and use for these combustion reactions. And the first is the difference between wet bases and dry bases. Wet basis refers to the fact that mole fractions are computed including water in the calculation. So this is what you would normally think of as your composition is on a wet basis. It includes the water that's present in that stream. But often the compositions are given on a dry basis, that these are the mole fractions that are computed without water in the calculation. And the way we handle that in the past problem is that when we were told that we're given compositions on a dry basis, is that we hypothetically separated the water out as a separate product stream, and it treated the dry gas as another product stream. So we took the actual product stream, which is a wet gas stream, and treated it as two product streams. The theoretical air is the amount of air that contains the amount of oxygen that's required for complete combustion of all the fuel. So to do this, we most likely will compute the amount of oxygen required for complete combustion, and then from the amount of oxygen we'll calculate the amount of air, because we know that there's 100 moles of air for every 21 moles of oxygen. Percent excess air is similar, the calculation of it is similar to how we calculate percent excess of any reactant. It's the amount fed minus the theoretical amount divided by the theoretical amount times 100. And for these combustion reactions, we'll usually use atomic balances, almost always. So here's the first problem. We have a mixture of two hydrocarbons, propane, which is C3H8, and butane, which is C4H10. It's burned with pure oxygen. So here's an example in which we don't have nitrogen present. We're burning this with pure oxygen. We're told the product gas from this combustion contains 47.4 mole percent water on a wet basis. So 47.4% of the product is water, which means the balance is the dry gas. So after the water is removed, the dry gas contains 69.4% CO2 and the balance is oxygen. So this dry gas contains only CO2 and oxygen. What we're going to do is from the information we're given here, calculate the mole percent of propane in the feed and what the excess oxygen is. To do this, what I'd like for you to do is pause this presentation after we finish the problem statement, draw and label a process flow diagram, and balance the combustion reactions. So please, stop the presentation now, stop the lecture now, and draw and label a process flow diagram and balance the combustion reactions. So I hope you took a moment in order to draw the process flow diagram, label the streams, and then balance the combustion reactions, and hopefully you ended up with what you see here. So first of all, here's the combustor, and inside it is written the two combustion reactions. The first is a reaction of propane with oxygen to form CO2 and water. And so in order to balance this, let's just assume that we have one propane reacting, and if we look at the propane, there are 3 carbon atoms per propane molecule, so that would imply we have to have 3 CO2 molecules over here in order for the carbons to balance. Since there are 8 hydrogens, in order to have 8 hydrogens appear over here and with water, we need to have 4 water molecules. From the amount of oxygen on the right-hand side, we need to determine the amount of oxygen that needs to react with that one propane. And we find that there are 6 oxygens that would be present in the CO2 plus the 4 that are in the water. It gives us 10. So we need 5 oxygen molecules to provide the 10 oxygen atoms. Next, let's look at the butane. Butane is C4H10. It's going to react with oxygen to form CO2 and water. If we were to put a 1 here for the coefficient for the butane, we need 4 CO2s over here to contain all the carbon. So this has actually been changed to 2 and this to 8. We multiplied both those numbers by 2 in order to avoid a fractional oxygen coefficient here. But let's just presume this is 1, and then if the coefficient here for butane is 1, then the coefficient over here for CO2 would be 4. In order to balance the hydrogen, there would be 10 hydrogens here. We'd have to have 5 water molecules over here in order to balance the hydrogen. And if we were to calculate the amount of oxygen, we would have the 4 times 2 is 8 oxygen, plus the 5. We'd have 13 oxygen atoms that we'd need. So we'd need 13 over 2 oxygen molecules. So that's why we multiplied by 2. So we multiply 13 over 2 by 2, we get 13. We multiply the 1 here by 2 to get 2. The 4 we had here is multiplied by 2 to give 8, and the 5 we had here is multiplied by 2 to give 10. I know that's maybe a little difficult to envision, but why don't you write it out and do it yourself. Now I think you'll be able to confirm that. In terms of the flow rate of the feed hydrocarbons over here, we're told nothing about. We're not told the flow rate nor the composition. So we write down N1 for the flow rate, X1 for the composition of the propane, and 1 minus X1 the composition of the butane, since these two have to sum to 1. We're reacting it with pure oxygen, so the stream, which we don't know the flow rate of, or label the flow rate as N2, and the mole fraction of oxygen is 1. The stream over here is N3, and we're not given directly for the stream much information about the compositions here. We're going to add that in later, but let's presume that we don't know any of this. We're not going to use that information we're given. So let X2 represent the mole fraction of oxygen, X3 represent the mole fraction of CO2, and 1 minus X2 and minus X3 be the mole fraction of water. Actually, we do know that this is 49.4% or 47.4%. So let's presume we didn't put that information here. What I'd like for you to do is to do a degree of freedom analysis for the process flow diagram as shown. To do this for atomic balances, what we're going to do is count the unknowns and subtract from it the number of independent atoms that are present in the reactive molecules, subtract from it the inerts, and subtract from it the specs. Now remember, we do have those 2 specs. We're told the composition of water in the wet gas, and then we're also told the composition of CO2 in the dry gas. So we're going to sum these all up and see how many degrees of freedom there are left over. So please take a moment and do this degree of freedom analysis now before moving on. Well, I hope you took a moment to do this degree of freedom analysis. Let's go through and examine what you should have gotten. First off, we're going to count the unknowns. We're going to start with the hydrocarbon feed stream over here. If we count these using the total flow rate and the compositions, what we find is that there's, in terms of the ends, that there's 1 unknown flow rate and 1 unknown composition that we need to include in our list here. If we look at the oxygen, we have another unknown flow rate, so we have a second unknown flow rate we need to include. We do know the composition of oxygen, so there's no additional unknowns from that, so we're up to 3. Over here, we find is that there are 3 more unknowns. We have 1 more unknown flow rate, gives us our 3 unknown flow rates shown down here. We have 2 more unknown compositions, X2 and X3, which when combined with X1 gives us the 3 unknown compositions shown down here. So we have a total of 6 unknowns. Next, let's count the number of atoms. And since this is a hydrocarbon reacting with oxygen, we have 3 independent species. We have carbon, oxygen, and hydrogen. There's no sulfur present, so we won't include that. So we'll subtract off 3 from that sum, and when to do a degree of freedom in our sum to do our degree of freedom analysis. There are no inerts. We have pure oxygen that's being fed, so there's a 0 here. In terms of the specs, we're told how much water there is and also how much CO2 there is in that stream. So we have 2 specs, so we'll have to put a -2 here. If we sum this up, we have 6 minus 3 minus 0 minus 2. We have a +1. So we have 1 degree of freedom. We're going to use that degree of freedom to set a basis, and we're going to use as a basis the wet gas flow rate coming out, the total flow rate of the stream coming out. We're going to set that equal to 1. But since we're also given some composition data for the dry gas, what we're going to do is we're going to redraw this process flow diagram. So instead of having 1 stream coming out here, we're going to have 2. We're going to have 1, which is just the water only, It's 47.4% of that total of the 100. The other, which would be 100 minus the flow rate of the water, that would be the flow rate of the dry gas stream. The composition of CO2 in that dry gas stream is 69.4%. I want you to take a moment now and redraw this process flow diagram. In particular, the product stream coming out over here. Replace that with two streams, one which is the water, another which is the dry gas, and label those streams given the composition information you have down here. And also, what I'd like for you to do is to rewrite the stream information that's given in the process flow diagram in terms of not the compositions and the total flow rate, but in terms of component flow rates, the flow rate of each of the components. I want you to take a moment and try to do that on your own before moving on, and I'll show you what I think you should have found. Well, this is what I think you should have found. First off, let's look over here at the hydrocarbon feed. So we're going to write NP to represent the propane in that, the flow rate of propane in the stream, and write NB to represent the flow rate of butane. Since this stream is pure oxygen, the flow rate of oxygen is just going to be equal to N2. It's 1 times N2. Now up here, we could also write the flow rate of propane as the mole fraction, which is X1 times the total, N1. Or we also can write the flow rate of butane as the composition of butane, which is 1 minus X1 times the total. But we're going to use NP and NB instead. Now the product stream, the stream produced by the combustion reaction, we're going to split into two. The first is just the water, so the composition of the stream is going to be, of water in the stream is 1. We're told 47.4% of the total gas that leaves, so of our basis of 100 is water. That's the composition of it, so we'll put the total flow rate is 47.4. The composition is 1, so the flow rate of water in the stream is 47.4, 1 times 47.4. The dry gas stream is going to be what's left over when we take away the water. So we assume the basis of 100 for the wet in total. We subtract off the water, 47.4, we end up with 52.6. That's the flow rate of the dry gas. We're also told the composition of CO2 in the stream is 0.694. So the flow rate of CO2 is 0.694 times 52.6, which is 36.5. Composition of oxygen is just going to be, since it's the balance, is 1 minus 0.694, it's just 0.306. The flow rate of oxygen in this stream is going to be the composition times the total flow rate, 0.306 times 52.6, which is equal to 16.1. So this diagram now is fully labeled. What I'd like you to do is to write out the atomic balances, the balances for carbon, hydrogen, and oxygen, and see if we can solve for the unknowns here. We have 3 unknowns. We have the flow rate of propane, the flow rate of butane, and then the flow rate of oxygen, which is N2. Well, I hope you took a time in order to write out the atomic balances before moving on in the lecture. Hopefully you ended up with the results as you see here. First, let's look at the carbon balance. What we're going to do is compute the amount of carbon that comes in and set it equal to the amount of carbon that comes out. We'll do that by looking at each of the streams that come in and calculate the carbon flow rate with those streams and set it equal to the flow rate coming out in each of the product streams. So first, let's look at the hydrocarbon stream that comes in. There is carbon that comes in with the propane. There are 3 carbon atoms per propane molecule, so we'll take 3 times the propane flow rate. We're going to add to it 4 times the butane flow rate because there are 4 carbons per butane molecule. There's no carbon associated with the oxygen coming in, so that completes our calculation of all the carbon that comes in. We'll set that equal to the carbon that comes out. There's no carbon that comes out with the water, so there's no contribution from that stream. The stream here, carbon comes out only with the CO2, so we'll take the flow rate of CO2 times 1, which is the number of carbon atoms per CO2 molecule. So we'll set this equal to 1 times 36.5. This equation involves 2 unknowns, the flow rate of butane and flow rate of propane, so we can't solve for either one. Let's move on. Hope we can find another equation that allows us to solve for one of those 2. Let's move on to hydrogen. The hydrogen flow rate coming in, we'll have to compute for the hydrocarbon stream for each of the components in it. So for the propane, there are 8 hydrogen atoms per propane molecule, so we'll take 8 times the flow rate of propane. Or add to it the hydrogen flow rate associated with butane. Butane has 10 hydrogen atoms per butane molecule, so we'll take 10 times the flow rate of butane. There's no hydrogen that comes in with the oxygen, so this is the total hydrogen coming in. We're going to set that equal to the hydrogen that comes out. Look at the water up here. There is hydrogen that comes out with the water. There are 2 hydrogen atoms per water molecule, so we'll take 2 times the water flow rate, which is 47.4. There is no hydrogen that comes out in the dry gas. There's no hydrogen in the oxygen or CO2. So this is the total hydrogen that comes out. So 2 times 47.4 is just 94.8. Unfortunately, these 2 equations, we cannot solve for propane or butane, the butane flow rates by themselves. We're going to solve those 2 equations simultaneously. I'm not going to go through the process for doing that, but if you do so, you find that the propane flow rate is 7.1 and the butane flow rate is 3.8. Once we know those 2 flow rates, we can calculate the mole fraction of the propane. It's just the propane flow divided by the sum of the propane and butane flows, which is a total. Doing this calculation, you find the mole fraction of propane is 0.651, or it's 65.1% propane. Let's move on to the oxygen balance. We're going to set the oxygen flow rate coming in equal to that which comes out. There is no oxygen that comes in the hydrocarbons. The hydrocarbons contain only carbon and hydrogen in this case. Oxygen does come in with the oxygen molecules, the other feed to the combustor. There are 2 oxygen atoms per oxygen molecule, so we'll take 2 times the flow rate of oxygen, which is N2. And set that equal to the oxygen that comes out. Turns out there's 3 contributions to this, to what comes out. There's 1 from the water. There's 1 oxygen atom per water molecule, so we'll have 1 times 47.4. We'll add to it the oxygen flow rate, the oxygen atom flow rate associated with the oxygen molecules that come out. There are 2 oxygen atoms per oxygen molecule, so we'll take 2 times the oxygen flow rate, oxygen molecule flow rate, which is 16.1. We'll add to it the oxygen flow rate associated with CO2. There are 2 oxygen atoms per CO2 molecule, so we'll take 2 times the CO2 flow rate, which is 2 times 36.5. If we combine these, we do this addition right here and then divide by 2, we find that the N2, which is the oxygen flow rate coming in, is 76.3. To compute the excess oxygen or the excess air, we need to calculate the theoretical amount of oxygen that's needed. The theoretical amount is going to be the amount needed to the amount required to completely combust all the propane and all the butane. So to compute the theoretical amount, we're going to take the propane flow rate, which is 7.1, and then multiply by the amount of oxygen that's needed. There are 5 oxygen molecules required per propane molecule. So we're going to multiply this by 5 over 1. We're going to add to it the butane flow rate, which is 3.8, times the amount of oxygen that's required. We know from the reaction stoichiometry there are 13 oxygen molecules required per 2 butane molecules. We're going to multiply this by 13 over 2, the ratio of stoichiometric coefficients. If we perform the math that's shown here, we find that the theoretical oxygen is 60.2. So we can calculate the excess by simply taking the amount of oxygen that was fed, subtracting the theoretical amount, and dividing it by the theoretical amount. We can do this either for oxygen or CO2. If we put in here the amount that is fed, which was we calculated as N2 is 76.3, subtract off the theoretical amount, which is 60.2, take that difference, divide by 60.2, and multiply by 100 to get the percent. We get 26.7%. This is a problem we're going to work in class. In this particular problem, we have the product gas from the combustion of a solid fuel has this composition that you see here, this molar composition. And in this particular case, it's on a dry basis. In this particular case, pure oxygen was fed in 20% excess. The question is, what's the elemental composition of the fuel? We're going to assume that there's no oxygen in the fuel and that there are no liquid or solid products left after combustion. So perhaps you could spend a few moments, a little bit of time, thinking about how you would approach this problem. I would start off by drawing a process flow diagram and try and label it given the information you see here.